So today, with our notes, we're going to be talking about equilibrium. So the first thing is if you guys want to bring out your notes and follow along with us, you can. It's underneath your class page. I'd recommend it as we go through it. So what we want to first start off with is our definition for equilibrium. Now with equilibrium, that's going to be the state at which the forward and reverse path of a physical or chemical change takes place at the same exact time. When you see chemical equations, we used to have something that looked like this before. We had something on this side, say like something plus something yielded, and we gave one arrow something plus something. Now what we're saying is that we can have a forward and back reaction. So now we can say something plus something could go one direction
or the other
to equal this plus this. And we're saying this side could also go back and form the reactants. So we're saying the products and reactants go back and forth to recreate all their stuff. Now I might be saying to me, Miss Trevor, what do you mean? That kind of sounds kind of wacky. How could something that reacts, that makes a chemical or physical change, go back? If I were to do like those combustion reactions, I burn the paper. The paper can't go back. We talked about at the beginning of the year, chemical changes are something that isn't reversible. Well, it wasn't reversible without adding extra energy. Now, there's this wonderful thing called an iodide clock. And this stuff is really, really cool. So I'm stealing this video. I'll show you guys the link to the video in a second. I'll also be posting it in here. But after you mix two chemicals together, we can see, if you watch here closely, after he mixes the two chemicals in. So watch as it goes. And after a couple seconds, the reaction will... I missed it. Oh man, I thought it was going to be so cool. Right there. It changed from clear to black. Now after a little bit more time, it's going to react, and it's going to be going back to that clear color. Oh, it's not going to show in this video. But if you let this reaction run even longer, it'll keep going back from clear to black to clear to black. If you want to know, there's a chemical experiment, 28 iodine clock, from that person, covering over all my bases so I don't steal information. So these are going to be reactions that happen both going to go from products to reactants, reactants to products, and keep going back and forth until we reach a balance. You can imagine this as if you had if you were like do a cannonball into a pool, you see the waves go out, and they hit the wall of the pool and they come back and they keep going out until they level out. That's exactly what equilibrium problems are going to do. Right when you set the reaction, it's going to send that wave out. It's going to hit stuff, keep going back and forth, keep moving, until at some point it's going to equal out and stop reacting. The first one we're going to talk about is physical equilibrium. If a physical equilibrium takes place, that means the same rate as an opposite opposes the physical change, then physical equilibrium is reached. This is just like if you had water and you freeze it. At one point, it'll start reacting, going through phase changes to form a solid of ice. Or if you go in the reverse, you know that liquid ice can go back, or solid ice can go back to liquid. Same with water going into gaseous water, and going from gaseous water back to liquid water. So these are some examples you can always do. So going from freezing to liquid state, or solid to liquid, liquid to gas states are all examples of this. You guys probably can have a lot of different ones, like melting metal is another form of physical equilibrium. At one point, you're going to have chunks of solid pieces in there. How many of you guys have melted butter before?
Me.
I have.
Yeah.
I have.
So, have you ever put it in there? You guys saw it melting, and as it's melting, you can see that bar of butter still in there. Although there's still liquid there, there's still some solid part to it. Right? You guys have all seen that before?
Mm-hmm.
Yeah.
That's a form of physical equilibrium. We have some parts of it as a solid still, the other parts as a liquid. Now, have you ever taken it off and just placed it on the side just to let it harden again?
Yeah.
Because at that point, you're going in the reverse. You're going from a liquid back to a solid. But as you're going there, there's still that liquid and solid mixture still being in there. So it's just that state at which you have the reactant when it can go either way in a reaction. Is that making sense to you guys so far?
Yeah, that makes
Yes.
sense.
Cool.
That makes sense.
You guys good on this stuff with your notes if you're following along? Can I move on with that stuff or want a minute
Good.
to finish it down?
I'm good.
I'm good.
I'm hearing goods. Lillian, Mitchell, you good?
Yep, I'm good.
Awesome. So chemical equilibrium. This is my favorite stuff of the equilibriums because chemical equilibriums have such cool reactions. So most reactions are reversible. Now, a reversible reaction is a chemical reaction in which the conversion of reactants into products and the conversion from products into reactions happen at the same time. So we have a second to get that down because I want to show you guys something in a painting like I was doing before. Okay, so I'm going to show you what I mean by this. It's just like in that video we just watched, how we had that beaker. Actually, I'm gonna draw it. The Erlenmeyer flask, I'll actually keep it the same. In the Erlenmeyer flask, we had a liquid in there, and we added another clear liquid into there. We actually had it go, and after they mixed together, we had both the mix in there where we had, what color do you want the iodide to actually make iodide purple? Because it is purple, not red.
I was just about to say red.
It's purple. It's, when you see iodine in the stores, that's for cuts and stuff. We'll make red the other one. If you really want iodide to be red, you can imagine it there. So what's happening is these two molecules are starting to bond together. So you have one molecule and two. As we talked about reaction rates, they're going to start colliding together in these reactions. When they collide, they start to bond together. And when they start bonding together, they form a different color. So after all this stuff in here starts to react, we get it to form. This is a terrible Erlenmeyer flask, so forgive me. Again, not an artist.
Crap.
This stuff now is fill tools. Nice. Now it turned black. That means the majority of the molecules are like this. They are in the state where you have one connected to another. Now, after a little bit of time, when these molecules are bouncing all the way around the glass and bouncing into each other, so we have multiple of these ions, or compounds, I should say, not ions, compounds. No, let me move it. I'm a professional. So after we have this, and this guy comes over, he's bouncing around like crazy on the walls, and he goes bang and hits this. What happens is there's a chance where they can actually break apart, and they react again to give us the individual parts. So these will separate again. And when this happens, we go back to what we started as. So then we'll have a clear liquid with our red dots and our purple dots just all mixed together. And that's essentially what chemical equilibrium is. Now, that being said, eventually the rate of the forward reaction will equal the rate of the reverse reaction of the system, and they will reach equilibrium. That means, as our example of the iodide clock, after a while of it going back and forth, back and forth, back and forth, it'll stop in one stage. Now, it usually stops in the reactive phase where they're combined, forming that black liquid that you saw there. Another example will be like sulfur. The sulfur ions down here in the oxygen leading to sulfate. You'll see those react together, and it will eventually land on one then the other. Making sense so far?
Making
Oh, yeah.
sense.
You guys got it?
Making sense.
Good to move on?
Yep. Mm-hmm.
Yep.
Awesome. Now we're going to talk about factors that affect our equilibrium. Now, chemical equilibria changes depending on conditions. Conditions mean everything in chemistry. Being under certain conditions may allow you to have reactions or not have reactions at all. So when a change is introduced to a system in equilibrium, the equilibrium shifts in the direction that will reveal the change. This is known as the Le Chatelier's principle. Le Chatelier's principle, it allows us to predict how a system will be affected by three most common factors. And this is where we're going to be doing practice on this tomorrow. I have a short worksheet of reading a reaction thing and identifying which part of Le Chatelier's principles are being applied there and which direction will it be shifting the reaction to. I might jazz it up a little bit and give you guys some balancing questions in there because I feel really confident in your balancing skills now. So that'll be part of it tomorrow.
So La Chatelier's principle, it allows us to predict how a system will be affected by the three strongest reactants.
Well, no, it's just the thing above it. It's when a change is introduced to a system in equilibrium, the equilibrium will shift in the direction to relieve the change. That's this part right here. Actually, I need a pointer. This part right here is the definition for Le Chatelier's principle. This is what Le Chatelier's principle allows us to do in chemistry, the bottom stuff here. And there's three factors. How many people can guess what the three factors we're knowing about reaction rates? Going back to that knowledge, which do you think are the three we're going to be talking about? We're going to make guesses now.
Ooh. Like the like a product or like
No, like what factors do we change? Such as like, remember the popcorn experiment? What did we change there? Those are the kind of reaction rates. We saw how
Oh.
fast or slower they reacted. What were some of the things we talked about?
heat, temperature.
Temperature
and-
could be one. What else?
Would amount be one of them?
What was that, Lillian?
Quantity or like amount?
Concentration could be. All right. So
Oh, and
go ahead.
the moving factor, like when you move the popcorn.
Okay, could be, yeah, could be motion. Kinetic energy, as we call it. Okay, so let's go on. The first one, like Mitchell got right on the point, is temperature. There are two
Do we
types.
have to write all that down?
I would look at the underlying stuff because I'm asking what happened here. So if temperature in the reactant side increases, then the equilibrium shifts to the products to use the heat. So I would look at the second tab here. So if heat is added to the equilibrium, it'll shift to remove the heat from the reaction. Chemical reactions usually don't like heat because when you add heat into it, you're increasing the amount of energy to it. When you're increasing the energy, they're making those electrons shift those stages. Like remember when we did our Bohr models, how we had those electrons in there? when they kick them up to the next energy level, they are not happy. They want to be back in their ground state and not wanting to lose or gain electrons. They want to be happy with their shells. So whenever you add heat into it, if you add it on the reactant side, you'll have more of the reactants reacting together to form products. Because if you look on here, there is no heat on the product side. Much like how in the summer days, if you're outside on a 100-degree day, or you can be inside where there's air conditioning that's like 60 degrees, you guys are probably not going to want to stay outside in the boiling heat. You want to be inside where it's nice and cool and you feel comfortable. The same thing acts with the elements in the reactants and products. So on the endothermic one, the reactants have heat on this side, so it forces it to make more products. Exothermic reactions have the heat on the product side. This makes the temperature want to make more of the reactants. So if temperature is produced on the product side, then the equilibrium shifts to the reactants to use up the heat. So just like you guys being outside. I like that example the best just because it makes a lot of sense. Because if you're outside and you're really hot, you want to be inside where it's nice and cool. And if it's too hot in your house, you want to be outside. Any questions so far in this stuff?
No.
No.
You guys got a copy down in your notes and stuff, or you need a second?
I
I'm
need
good.
1 second.
1 second. All right. So you have 1
Because Jazz
Mississippi.
writes down
So you
everything.
ready, Jazz? Get it?
Yeah.
I asked you for 1 second and gave you 1 second.
Yeah.
Now just tell me when you're ready.
Okay.
I'm good.
I got down the exothermic and endothermic. I'm good.
Okay.
Okay, I'm good.
Okay, Mitchell, you good?
Yep, I'm good.
Okay. I just didn't hear you say anything, so I was assuming you're ready. The next one is concentration. Again, the underlined stuff is what you're going to be really looking at for the answers for those notes. So concentration. So if the reactants has a higher concentration than the products, the equilibrium will shift to the product side to relieve the increase in concentration of the reactant side. The opposite will happen if you have more concentration of the products. The equilibrium will shift to the reactant side to relieve the increase in concentration of the products. For concentration, I have this as in you're in a crowded event. So let's say if you're at a concert and you have either the left side of the stage or the right side of the stage to be on. You get told you need to stand at the left-hand side of, or you chose to stand the left-hand side of the stage. And then, as the concert keeps going, you have now everybody. You have about, let's make up a number, out of a 600-person concert, 500 of them stand on the left side of the stage. Now, will you be able to see anything happening on the left side of the stage? Probably not. If if you're sitting with 500 people, it'd be hard to see. Now, if you go, you would want to move to the right side of the stage where there's no people there. So that's just like how it's easier for you to see and view stuff. That's what we're talking about here. I know this example wasn't my best one, but it's just the one that I thought of off the top of my head. Is the easiest way of looking at it for me. Is in a crowded place, I usually like to take the area where it will let me see the best. You guys understand concentration?
Yeah.
Can we move
Pretty
on from
good.
it to last one?
You're posting this again online, right? Later.
Online, yeah. This will be a YouTube. This is a YouTube video that is going to be posted online. I am recording
Yeah.
it right now, so you guys are part of the YouTube video.
Because my dad kind of interrupted. And I
It
kind of
doesn't
missed
matter.
the whole thing.
So last one we have is pressure.
Pressure.
Ooh.
Pressure is one
Missed
thing
that
that
one.
affects a lot of reactions. No, if a reactant has a lot of gas particles or pressure, this will shift it to the product side to relieve the increase in gas particles on the reactant side. The same thing will be said about the reactants to products. If products have the gas have more pressure, then it'll shift it to the reactant side. How many guys have ever tried playing with like those jelly blocks? Like, you know, they're kind of not like Jello, but like they're like the jelly blocks that kind of like squishy. You can move them around, but they always come back to their form.
Yeah.
Mm,
You guys know what I'm talking about, or would you like to see a picture of it?
I would like to see a picture of that.
Jelly
I'd like
blocks.
to see a picture of
I
it.
have no
Yeah.
idea what you're
Okay.
talking about.
So these are like this. Oh, well, okay. No, I'm getting somebody's documentary on their experience. I'll just show you the picture. So like this stuff. You kind of like
I've
poke
seen
it
it.
and like it kind of jiggles.
Yeah.
I've never
Okay.
played with it, but I've definitely seen it.
Yeah.
What
So have
about
you
the
ever
Tetris
tried
cubes on
pressing on it? What happens? Or like the Jello blocks, like the building blocks like
Oh
this.
yeah.
It's another thing.
It like pushes against you and like goes back to its original form.
Yeah, and like if you press on like the far left of it, kind of like shoots out, right? It kind of like
Yeah.
slides away from you. That's exactly how pressure is in chemical reactions. When one side has too much pressure on it, let's say we'll make our Jello block. If we put a lot of pressure on here, and we're saying this is the reactant side, and this side's the product.
Makes the
If
other
we
side a little bit
press
bigger.
down here, the Jello block's going to want to shift over to the product side, right?
Mm-hmm.
Yep.
And the vice versa. If we take our Jello block and we press on the product side, it wants to shift over to the reactant side, right?
Yes.
Right.
The same thing happens with the chemicals. If you want to put more pressure on the reactant side, it forces it to go over to the product side. And if you put more pressure on the product side, it wants to go back over to the reactants. That's all it's saying for there. And that's pretty much it for our lesson for today. Do you guys have any questions, comments, or concerns?
No, that was pretty good.
All right.
We're good.
Very good.